Okay. Okay. Hi, everyone. This is the seventh lecture. We continue to talk about recursion, and recursion is still covered in 165 and 210 at DVC. So we can do a little review of recursion from the last lecture. So we have learned about two types of recursion, and one is tail recursion. The structure of tail recursion is only base case and recursive call. And the last operation of the tail recursion is the recursive call. So that's why it's called tail recursion because um, the recursive call can be the tail of the program, of the function. And the last one is it can use the nested function to do aggregation in tail recursion. For common recursion, so the structure is we have base case recursive call, and we also have aggregation. Aggregation is to combine recursive calls. So the last operation of the recursion frame is the aggregation. So after we call recursive call, the old function will not close. The old frame will not close, but we still open new frame. So after we return something from the new frame, and we will do the let the result combine together. So this is the aggregation, and this will be the last operation of a recursive frame. And the last one is to apply recursive call, to apply recursive leap of faith, so that you can try to know how to aggregate with the return result and also your input or maybe something else that can help you finish your goal. Okay, so the recursion and iteration. Recursion and iteration. Recursion can be converted into iteration and vice versa because recursion and iteration they are both try to execute the same codes many times. So they are actually very similar. And if you want to solve recursion problem, you can try write something in iteration and then convert it to recursion. So how's that? Why would that be very similar? We can see from the structure. So on the left side, this is recursion, and on the right side is iteration. So um, we have defined if, else if, so this will be the base case. And what will be the base case of the while loop? The while loop is like I have the condition. So when the counter cannot satisfy with the condition, it will stop the while loop. So this can be the base case for the while loop. So this is the base case part. The while loop condition can be the base case part of recursion. And the second, we have recursive call. So how can recursive call be achieved in while loop? So we also have the counter, and we also have something that we may want to change. So we have the counter n is n followed by 10. So it will make the variable n smaller and smaller until hit 0. So this is the condition, a counter. Uh, it will be changed in order to narrow down the while loop execution. So this can be the recursive call part of a while loop. So to narrow down the counter and the aggregation. Aggregation is that some like in recursive function, we have the aggregation combined with the recursive call and also something maybe input or something else. So we can combine it together to return our result. So in while loop, we can have a variable. So every time we go past this variable assignment line, we will try renew the value of the variable again and again. So it can be either accumulated or just be changed many times using the same logic. So this can be the aggregation in the while loop. So how to solve the problem, how to change the solution variable many times so that you can return uh, the correct result. So it's the same as in recursion. Yeah. Okay. So recursion. There can be more than one recursive call in aggregation part of the frames. So from last lecture, we only do recursion with only one recursive call. So in tree recursion, we have more than one recursive call, basically 3, 2, 4, etc. And then it can be used to solve more real questions. What kind of questions we'll talk about later. And since every time an old frame opens more than one new frame, and the old frames keeps open, so the frame connection will be very gorgeous. We can show it using a diagram. The diagram looks like a tree, so we call it tree recursion. So coming with an example, um, the Fibonacci sequence. The Fibonacci sequence is a very special sequence, and in math, discrete math, and computer science. So, what is the Fibonacci sequence? Fibonacci sequence is the element of the sum of the previous two elements. So, I have the basic two variables, basic two numbers, 0 and 1. And for the third one, I will come from 0 plus 1. So I get 1. For 2, I have 1 plus 1, get 1. 1 plus 1 is because 2 is in the fourth place. So the result comes from the second and third place, which is exactly um, the number right in front of 2, or the uh, number of number in front of 2. So I have 1 plus 1 to be 2. And for next one is 1 plus 2 to be 3. And 1 plus 2 plus 3 will be 5, etc., until I get so many. So we have like 0, 1, and 0 plus 1, 1. 1 plus 1 is 2. 1 plus 2 is 3. And 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13, etc. So uh, if I want to find the sixth element of the sequence, how should I do? Like, I mean, on paper, if I try to like draw something on the paper, on a sketch paper, we can try drawing the diagram. So, so I'm gonna like, I have a diagram here. So it's fib 6. So to convert it into fib 6, like we have Fibonacci of 5 plus Fibonacci of 4. So which means um, I can partition the Fibonacci of 6 into Fibonacci of 5 and Fibonacci of 4. So Fibonacci of 5 plus Fibonacci of 4 returns Fibonacci of 6. And then I have 5. We can change 5 into 4 and 3, change 4 into 3 and 2, and change also to break it down. Fibonacci of 4, break it into Fibonacci of 3 and Fibonacci of 2. And Fibonacci of 3 can be 2 and 1. And Fibonacci of 3, 2 and 1. How about 2? Like, since it's the base case, so it already returned the result 1. So you do not have to break it down, because it's like we can't break it down anymore. So still break it down. 3. So I get this diagram. So I have Fibonacci 2, 1, 2, 2, 1, 2, 1, 2. So I can't break it down anymore, because it is already the base case, and we do know the result of Fibonacci of 1 and Fibonacci 2. Fibonacci 1 is 0, and Fibonacci of 2 is 1. So this is 1, 1, 0, 1, 0. So we just have to combine all of them together. So 1 plus 0, so this return 1, and this plus 1 return 2, and this returns 1. This returns 1, and the whole thing here returns 2. And also here, this plus this, so I'll still get 2, 2, 1, 1. Oh, this is 2, and this is 1. So I'll get 4 plus 3. So 2 plus 1. So it's 3. And 1, 1, 1, and 1, 1, 2. So this will be 5. If I do it right, uh, it's just 1 plus 1 plus 1 plus 1 plus 1. There will be 5 ones. So it's the result of Fibonacci of 6 is 5. So that's how we do it in math or by hand. So I'm going to do that by writing a program. So Fibonacci sequence. The base case is like when the input is equal to 1, it will return the input, I mean the place. Try to find Fibonacci of some place to see in this place what is the Fibonacci number. So the Fibonacci number of Fibonacci of 1, like in the place 1, the first place is 0, and then for 2 is 1. So this is the base case, and we can't break it down anymore. So we have recursive call. Recursive call is like when I have in a place Fibonacci is n, um, I can find the answer directly since maybe n is greater than 2. And so we know that Fibonacci of n minus 1 and Fibonacci of n minus 2, if I want to get Fibonacci of 2, I have to get these two, and then I will add them up together. So the recursive call is Fibonacci of n of 1, n minus 1, and Fibonacci of n minus 2. And this one is reduced by 1, and this one is reduced by 2, which fits in our definition of Fibonacci sequence. And then the next one is aggregation. Aggregation is very simple. We just have to add it up together. So we have Fibonacci of 1, n minus 1, plus Fibonacci of n minus 2. So this will be our aggregation. So by applying recursive leap of faith, we will know that Fibonacci of n minus 1 return the result where, like in the n minus 1 place, what the Fibonacci number will be. And also the same thing for Fibonacci of n minus 2. When I'm looking into the place of n minus 2, like the n minus 2 place, what the Fibonacci number will be. And then I will find all of them out together, and we just have add it together. So we can find the Fibonacci number at nth place. Yeah. So Fibonacci sequence. So I define Fibonacci of n. So this will be these two will be the base case. So n less or equal to 1. Suppose maybe sometimes maybe you have wrong input, which means n is less than 0. Then n is negative. I will stop it here. So we return 0. So else if n is equal to 2, so return 1. So which fits in our base case definition, 0 and 1. And else I return Fibonacci of n minus 1 plus Fibonacci of n minus 2. So this will be the base case. Base case when n is at the very beginning, Fibonacci sequence is in the very beginning, so have n equals 1 and n equals 2, so return 0 or 1. Or else when n is greater than 2. So I will have the aggregation, recursive call and aggregation. So this is the base case and the recursive call. By applying recursive leap of faith, I will know, like suppose I'm getting Fibonacci of 6. So this will be the Fibonacci of 5. I have to believe that, I have to assume that by applying recursive leap of faith. So I will see Fibonacci of 5. 1, 2, 3, 4, 5 is 3. So I will believe that this works very well, and then I will return the number 3, because this is the grand number for Fibonacci of 5. And this is the Fibonacci of 4. So I will assume that it return 2. So 3 plus 2 will be the Fibonacci of 6, which is 5. So this is the true recursion. we use the Fibonacci sequence to show one of the examples of tree recursion. Yeah, and then aggregation is like to add them up together. Like since I have no free path to, and then to get the answer, I just have to know. I have to add them up together, so I will get 5. Okay, so demonstration of it. Turn off. So yeah, so this is the Fibonacci sequence function, and then we show it. So I'm getting Fibonacci of 1. I'll get 6, and I skip all the base case. I go to the recursive call. So get Fibonacci n equals 5, and I'm executing the first one, and then I will break it down to 4, 3, 1, 2, 1. So I get when n is 2, so return value is 1, and then I return to here, frame of 5. So return here, and then I do the next one. I do Fibonacci. I get like 2 minus, so I get like 3 minus 2, which is 1. So from frame 4, actually return to frame 4. So get 0, then add them up to be 1. Then so break it down very little, and then find the base case, and then aggregate together, so that you get the answer eventually equals 5. Yeah. So efficiency of recursion. So recursion opens many new frames, and the opening frames occupy the efficiency of the running process. So if you try to apply recursion, especially for tree recursion, will be a lot of frames opening, and you may keep opening many new frames. So maybe the program or the computer cannot carry out very heavy work. And more efficiency scenarios will be discussed at the end of the course. Yeah, efficiency. We have a lecture about efficiency, including recursion, while loop, and other stuff. So tail recursion. For tail recursion, because the last operation of a tail recursion is the recursive call, which means that when opening a new frame, we will close the old frame. So eventually, when you go along executing tail recursion, you find that there will be only one frame opening all the time. So, I don't know how Google should recite this, but yeah, it's come to 1, and then suppose now we don't have a quarter or something, but yeah, what I mean is like it will be very few frame opening when you do tail recursion. So you close the old frame while opening a new frame. So all the time your frame will be only 1 when you execute the frame. If you have a nested function inside a function, and the nested function is a tail recursion, so maybe we have 2 frame opening together, because one of the frames will be the nested function, and the other frame will be the outside function. Yeah. So the common recursion, usually we have only one recursive call, so single aggregate. So which means that when you open a new frame, you keep the old frame still open. So which means that suppose here's the old frame, and I have to open new frame, but I will still keep the frame opening. And I have this new frame, and I will keep this frame still opening, and I will have a new frame. So which means that every time you open a new frame, um, you keep the old frame open, but there will be only one old frame opening for every time you exit this frame. So which means that the number of frames will go linearly uh, as the input amount gets bigger and bigger. So suppose I have the input amount is 10. So for tail recursion, it will be remain the same as the frame number equals 1. And for common recursion, um, I'll keep the frame opening, and then I will increase frame by 1 and keep this frame opening, and I will increase the new frame by 1. Yeah, so etc until I hit the base case, and then I will go back to 0. So because for common recursion, we only have one recursive call, so we only open new frame once. We only open one frame at a time. So it will increase accumulate, but only linearly. For recursion, however, it will be very exponentially. That's because every time you exit an old frame, you still keep the frame open, but you will open 2 or more frames. So, which means suppose I open 2 frames at a time. So this is the old frame, and I will still keep the frame opening, and I will have 2 frames. I will have 2 frames open, and 2 frames still open 2 frames, and the old frames still open 2 frames. So at this time, I will have 1, 2, 3, 4, 5, 6. Yeah, seven frames. So when you do the tree recursion, it will grow very fast, even going exponentially, because every time you have to you open 2 or 3 frames, and you also keep the old frame opening. So when you have the input amount which is very big, you may have hundreds, thousands of frames opening at the same time. So for tree recursion, it is very unfriendly to have a very large input, like maybe even greater than 50, 40. So when you do efficiency recursion, if you want to execute with larger input, it's better not to use tree recursion, but instead use memorization, maybe tail recursion or other recursion. So I have 2 methods here for solving the Fibonacci sequence problem. So when I use tree recursion, which is our example of tree recursion. So I get Fibonacci of tree n, and I still have 2 recursive functions, and I aggregate by adding them. So I use tail recursion, however, I use here, so I have the helper function inside, which will be the recursive function, and I will return helper 0, 1, n. So A and B will be, suppose I have 0, 1, 1, 2, 3, 5, 8, 13. A and B will start being 0 and 1 at the very beginning. And then I want to find the nth place, which means that I will move A and B going deeper into the sequence. So every time A and B will be new ones. So A will be B, and B will be A plus B. So for here, I store a new variable from here, and for B, I will still keep for the new A, I will put B into in so that it can move further and further. When the counter hits 1, which means that maybe I have nth counter and I decrement it by 1, so I execute maybe n times until I hit the base case, which means that the counter 1 base case means that we have to stop here because we already execute so many times, because every time we execute, we just move A and B variable by 1 every time. So that we hit the nth place. So we just return the nth place, the number in the nth place. So which means that we will eventually find the number of the Fibonacci sequence. Yeah. So I will do a quick example practice. So I have actually, yeah. So for here, I have Fibonacci of 1 and Fibonacci of 2. So Fibonacci of 1 is the tree recursion, And Fibonacci of 2 is the tail recursion. So we can try finding the efficiency of both of them, how they perform, and I mean how long they will perform to get the answer. So I'll go inside this. So I will try Fibonacci of 1 first. Fibonacci, the first, I'll try maybe 10. Yeah, I'll start from the beginning. So this is true recursion. It'll be 34. So for the second one, tail. Oh, it basically stem, right? Yeah. It doesn't mean like it, it doesn't seem to be memorization, like using the tail recursion will be better, but we can try larger numbers because 10 is eventually actually a very small input. We can try 40 this time. We use 3. Oh, I have to take some time. I don't know, like 1, 2, 3, 4, 5, 6, 7. Oh, I get a number, but like it'll take like at least 10 seconds to get the output of Fibonacci 40. So instead, this time I will use the tail recursion. Oh my God, it would take like 0.1 seconds, 0.001 seconds to get the output. So this you can see like the time difference between the two executions. This time I will get try having 100. I don't think the recursion will be so useless, but we can try. Oh, I'll wait. Uh, yeah, still waiting. Mm, oh, oh, the Ethernet agent crash. I think the program maybe crashed. Uh, it's running for so long, like maybe 30 seconds passed. Yeah, so I don't think we can get it like in maybe 1 minute or something. I choose to interrupt it. Yeah. So you see, like when Fibonacci 1 getting large input, it will be very slow until we lose the patience to wait for the answer. So it's just very unfriendly to both the computer or the user. For computer, it will break down kind of. For the user, it get mad. Yeah. I would patch over to 100. This will be the tail recursion. When I hit enter, oh, I get the number even like immediately. So this is the power of tail recursion, and I would introduce memorization later. So it's actually using the memorization because we choose to memorize like when we move A and B every time by 1, you store the new A, new B, and also decrease the count, the counter. So this is actually a kind of memorization. And yeah, but we don't have memorization in Fibonacci 1 because we choose to uh, load the frame to store our values. So the frame itself is very um, larger than storing the value, and maybe also because every time I duplicate new values into the recursive function, So which means that I do the memorization, but we didn't memorize our values in Fibonacci of one. So which means that if if you want to find the result of recursive code, you have to look very deeper into the frame, and it takes time. But for Fibonacci 2, since we duplicate it every time, so you can find the value immediately in the program. So if I for fun, I would do 900 because eventually I would not know. I would not know even though I do Fibonacci 1 of 100, I can get the answer. Um, so not to tell Fibonacci of 900. I can get Fibonacci of 900 with Fibonacci sequence too. So get a bunch of numbers. 33915. I don't know. Um, if I do 1000, uh, okay, well, it would say like repeat 995 more times. Okay, which means that the best like the greatest number I can find is 995. I can try 995. Yeah, wow. This is the greatest number we can find using tail recursion for this program. Yeah. So back to back to the slides. So when we use tail recursion and the memorization, like we memorize new A and new B and the new counter every time. Uh, we do the duplicates of them. So you will eventually know some result, even though it's very big, very large. So memorization. Memorization is like in recursion, you can use an auxiliary variable to store the answer of your every aggregation and then bring it into your next recursion. So the auxiliary variable, sometimes you don't have to actually only to store your answer, but you can use it to store your counter, you store your maybe new accumulated variables may not be the solution, but usually like for most of the time, you use auxiliary variable to store the solution. So which means that I actually do iteration, but using recursion though, like the logic is more similar to iteration. Um, than recursion by using recursion though actually. So we new define the factorial function and we have the helper inside, I have the counter and solution, and then I'll return. So when I return helper one, like because factorial is like you have to times suppose I do factorial 5, I have to times uh 5 with 4, 3, 2, 1. So the solution must be 1 at the beginning. It can be 0 because 0 times everything will be 0. So solution will be 1. And the counter will be the thing we have here. Like suppose I get with the number of 5, get with the number of 5, the counter will be 5, means that I will times the counter so many times, times with the counter I do the operation so many times. So I'll pass in n, and if the counter is less or equal to 1, which means the base case, like the base case of 1 is 1. Factor of 1 is 1. So return solution. Otherwise, I will duplicate. Um, I will find the new solution by solution times the counter. So sounds like 1 times 5. Yeah, and next will times 4, next will times 3, until 2 times 1. It's okay if when I get 1, I will return all these things. So this is memorization. What we actually memorize? We memorize solution by like you can think of it like by either creating a duplicate or just like passing something new to initialize it into the variable solution in the new execution of recursion. So solution counter, and we also do actually do the duplicate or do the memorization of counter like by degree by one every time. Yeah. So as I said, like although I say here like to store the answer of your every aggregation, it doesn't mean like you only use the actual variable to store the answer. You make something else like counter or something. Counter maybe also the Fibonacci uh, tail recursion. You store it with variable A, B, etc. Yeah. So and also the application of recursion. Recursion can be used for problems like eventually we get to this can be used to solve the problems in which you have to do very similar operations many times. But every time the operations can be slightly different. Um, suppose like every day I went to McDonald's and I'm thinking about to be something as my breakfast. Like the first day, I can choose whether to have a hamburger or the ice cream. And the second day, I will choose between these two as well. So we'll find how many ways I can have breakfast with maybe some or different types of hamburgers or ice creams. So every time I would go to McDonald's to buy my breakfast, this is a similar operation, but slightly different is that maybe I will buy something different. Maybe an ice cream, maybe a hamburger. Yeah. So for example, how many ways to have 15 cents? Like suppose I own a bank and I issue many coins. And if you want some coins, I can give you some, like as many as you want. And given arbitrary amount of pennies, like 1 cent, nickels 5 cents, and dimes 10 cents. So how many ways you can make it to 50 cents, 5 cents to using pennies, nickels, and dimes. So you can use 15 pennies, or you can use a nickel and a dime, and maybe use a dime and 5 pennies. Maybe you can use 3 nickels. So there are many ways to have 15 cents, but I want you to find how many exactly, how many ways exactly you can uh, bring the money together to have exactly 15 cents. So this will be solved by using tree recursion. And another thing is find a way to ferry 6 people from one bank of the river to the other with only using a boat with capacity of 3 people. So every time when I bring 6 people to the opposite bank, I will use maybe for the boat, I can carry 3 people. Like the people assume they are indistinguishable. Like maybe I have Trump in the one of the 6 people have Biden, but I don't count who they are. I would just say like I would choose 6 people are the same, and every time I would like take some people to the opposite of the bank, and how many ways? Like suppose for boats, the maximum carry capacity is 3, but I can only take 1 or 2 people to the other side of the bank. And how you arrange and how many ways of arrangements to make these 6 people to the other side of the bank. So yeah. So for these 2 problems, there is actually 2 types of problems, but they both use tree recursion. Why they're different? You have to think about orders of arrangement. So, do operational order matter? So, order arrangements may or may not matter, depends on the question. So, when you ferry 6 people to the other side of the bank, why is it? Why the order matters? So, suppose I do not carry 6 people. I only carry 3 people. So every time I have options like I will carry 3 people together to the bank, to the right side of the bank, other side of the bank, and maybe I will have two first, and then one, the remaining one. Maybe I have one first, and then two. Yeah, maybe that one, the first one, maybe Trump or something. Like maybe he has something, he tried to do something very quickly, is in urgent, so he'll go first. And this is the arrangement. Maybe I'll have one first and two second, and then I'll have one, 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 one. Yeah, every time only carry one person, like that distinguishable. So um, we only have we only counted one for this situation, like no matter who goes first. But for this case in between, between three and three ones, and two goes first, and then one goes behind, behind these two people, or maybe one of them goes first and the remaining two people go second. This shows the orders of arrangements, because if you want to carry two people to the bank, um, this matters because this will be different. This will be different. I carry two people first and carry one people first. They are different. So you have to think about like how to aggregate it during your program. And for the next one, it does not matter when you want to pay 15 cents with coins. Suppose yeah, suppose just 15 cents. It can be 10 plus 5. It also can be 5 plus 10. Suppose we were to think about orders of arrangements. 10 plus 5 and 5 plus 10 seem to be different, but actually they're the same, because when you go pay 15 cents, um, um, you give the cashier 10 cents first and then 5 cents next. Um, it's the same as you give the cashier 5 cents first and then 10 cents next, because eventually it'll be 15 cents. So for counting money, we don't have to think about the orders of arrangements. So they're also different. Yeah, because they kind of like having slightly different but mostly same. So the algorithms will be slightly different but mostly same. So if you are interested about it, like I do have different situations in my homework, and you can try doing it. Yeah, and then for the next one, I will practice. So practice counting ways to climb stairs. Yeah. So you have to think about whether the problem is um, the order is matter. The order matters. Maybe the order does not matter. So you think about it. So yeah, you can stop the video for doing the problem, but yeah, but I will talk about the solutions now. Yeah. So you say find how many ways to finish climbing some certain numbers of stairs. So um, assume I have a stair um, at at the DVC principal's room. Like I had to climb to see my principal. Yeah, and then okay, this is the room. Find how many ways I can reach the room. Yeah, first floor, maybe second. Yeah, and uh, so one person, like you can think about your daily life. When you grow climb stairs, you can only go one way at a time, or maybe you can go a big step, a great leap, like a leap of two stairs, and then go like that. Or you can do it like can try doing it alternatively. So one first, and then second step do six. I'll do two steps, and for final one, yeah. And so I already have found three ways. So I'm gonna do to define the function to find final way. Um, I will try opening the window. Yeah. Hey. Okay, so for now, I define the function. Suppose it's just called weights, and then a number of stairs. If if else. So if I only have one step, like I'm not gonna to have two. I'm not gonna to have two steps, right? So I would say like one of base cases. So like for safety, I usually use less than or greater to one. So just return one because there's only one way. I have two else if though. If else if else if else. So okay. So let's see. So suppose I have n is equal to one. Yeah. So I don't have two steps because since it's not necessary and it's impossible. So I will just say return one because there's only one way. Yeah. If I have two, how about if I have two? I can have a great leap to have two steps. This should be one, or else I'll have one step at a time. So this should be another one. So it will be only two ways to get to the stair with two stairs. Yeah. So n is equal to two. So return two. So how about no stair, no stairs? How about no stairs? So which means I only have zero, zero. Yeah. Uh, if n zero less than zero, return zero. Yeah. So let's see, we still have n equals zero. We left it. Uh, we'll talk about it later. So I will also have else if I also have else statement. So for else statement, for n is greater than or equal to three. So um, so for this guy, um, I I have one step at a time. Yeah, and I may have upgraded to two steps at a time. So in order to find how many ways left, if we reach here or if we reach here, um, I will have to assume that like in for this function from this step to the destination, I assume that it already return correct number of ways. So as you see here, I apply recursive leap of faith. So this one, suppose I finish stairs of two, so which means this is n of two. So when I find ways n of two, so it will return the correct ways. It return the correct ways when I go from this place to the destination. So also same if I go only one step, ways n minus one. So it returned the correct result, correct number of ways from this point to destination. So I have so many possibilities when when I already finished stairs of two, and I have that much that many abilities probabilities to after I step only one step. So the things I have to do that is like I will sum it together because I have so many ways. I have that many ways. So I compare that it will be the total ways of finishing these stairs. Yeah. So returning to this, returning to n is equal to one. So um, suppose I only have 3 stairs. So 3 minus 2, it'll be 1. So wait, suppose I have 4 stairs though. Uh, yeah, suppose I have 4 stairs. Yeah. Mm, I have to 2 minus 2 is 2, 2 minus 2. Wait, I think we already got this. Like it already fits in the result. Like suppose n minus like 3 minus suppose I come with 3. So so 3 minus 2 is 1, and 3 minus 1 is 2. So for only 1 stairs, I have 1 way. For 2 stairs, I have 2 ways. So adding up to be 3. So I did not suppose I did not get something less than 0 or equal to 0. But if I do n is 0, so if I have n 0 stairs, like I think I don't have any ways to find how many ways for completing stair climbing task because I can't even find stairs. So for n like is equal to 1 for this situation, I'll put it here. So for n less or equal to 0, I return 0. Yeah, I return 0. So ways, yeah. So this will be the answer. Yeah, this will be the answer, and I have the answer here. Okay, so count how many ways I have there. If I have a stair of 5, yeah. So the answer will be 8. Um, so every time when you do this, you open. I think I have to do a demonstration. So when I see, and I have 5, yeah, I would deduct it into n of less than like it all skip all the base cases. So I will return this. So for here, I actually started this frame already. So n is 3. So I'll get 3. So to find say this is a function w, so w3, and then I will still deduct it, and I'll hit. I will also have the first function. I will be w of 1, and then for this one, I return the value 1 because I hit the base case, so it's 1. So for here, I also have 2, and it turns out that it jumps into the function w of 2, and we also have the base case, which is 1 plus 2 for count way of 2. So yeah, return 2. So this will be 3. This will be 3. So and then I will have another frame. So I open it, it will be w of 4. And as you see, I will still deduct it like to w of 2 and w of 1. And then, yeah. So this will be 2, this will be 1. Wait, oh, this is 3. 2, and I also deduct here. So 2 and 1. Yeah. So for right now, I'm at this step because I already found out this is 3. I have this w count ways of 4. I'm having this step. So I'll deduct it into two first, run the left part, and I'll return two. Yeah, return two here. We are having this, and then we go return the aggregation of this friend, the aggregation of this friend. Then I will have this part. And this part is like when I put three, I'll deduct to two and one. So three. Uh, yeah, he will have one first though. Uh, same though, like because I do minus two first. So for n, next return one. So we return one here for this function, and then still doing this. So for n is two, return two. Yeah. Oh, I know why it's called tree recursion, because every time you partition, you partit like you bring the number into parts, and every part it will also bring the part to a smaller parts, and until you hit the base case. And then for the very last part, what you do is just to add all the results out together. Add add all the results out together. So for here, I will have 5 plus 2 plus 1. Yeah, yeah, we made it. It is A. It is A. So, okay. So, yeah. So why is it called tree recursion? Because when we start executing it, it will go deeper. Like it will partition the problems into so many parts. So until hit the base case, until they can be broken into parts anymore, because they hit the base case. When you hit the base case, you return the number, and then um, so it will add all the numbers up together, add all the numbers up together to return your result. So yeah, I think you can try drawing the diagram if you want to solve tree recursion using smaller input. Yeah, sounds like 5 or something, 5, 8, 10. Yeah, and for this problem, actually it is order matter, because every time when you step, when you have one step and then you have two steps, like in a three steps problem, like if we have one step and then two steps, and when you have two steps first and then one steps next, there will be two ways. There will be two ways, like because they end the same. They end the same. Um, so like it's a very typical problem for order matters problem. So you have to write every operations base case. Each of them will be the base case. And then for else, when you have some input greater than the base case, you have to make the choice. Suppose you are the one who try to climb the stairs. You have to find, oh, next step I will step two. I'll have two steps, or I'll only have one step. So you will have two possibilities, and then you apply recursive leap of faith to think that like the count ways when I step out this, it will return the correct result of me from the new step place to the destination, as the same for this one. So we have uh, so many so many ways after I step out two steps, and I have so many ways when I step out only one step, and I will add them all together. So this is the order matter solution algorithm. If you want to try order does not matter one, like I think it's harder to understand, but they will be usually mostly the same. Yeah, you can try in my homework. Mhm. So yeah, so that's it for today. Have a nice rest of the week and try to do homework. I also have my solutions in my GitHub, and you can try check it out. Yeah, right. Thank you.